Hi, everyone. My name is Melissa Foley. I'm a science director at the San Francisco Estuary Institute in our Resilient Landscapes program, and also co-lead our urban nature team at SFEI. And really happy to be here today. I worked on the Elwha Dam removal for a number of years, so happy to be talking with a group from the Salish Sea. And Alicia, I'll turn it over to you.
Yeah, sure. Hi, all. My name's Alicia Gilbreath. I've been working with SFEI for 18 years now, and now I lead the stormwater monitoring program for SFEI. Mostly, we do a bunch of monitoring in the urban tributaries surrounding the bay, but we also do a little green infrastructure monitoring. So that's why I'm part of the presentation today.
Great. So today we're going to focus on a project called Next Generation Urban Greening, which is a project in the city of San Francisco. This project was funded by the US EPA and the Water Quality Improvement Funds. And we have a number of other staff at SFEI that are also contributing to this project and making it possible. Right. So before I jump into the project, though, I wanted to take a step back. For those of you who don't know the San Francisco Estuary Institute, we are a nonprofit organization that delivers place-based science with the goal of informing management decisions around the region. We've been around for about 30 years. We have 75 staff across a range of different disciplines. And we have 3 different programs within SFEI. Clean water, which is where Alicia sits, environmental informatics, and then resilient landscapes, which is where I sit. And just to note, our clean water program is where the 2 of our long-term monitoring programs, the Bay Regional Monitoring Program for Water Quality, as well as the nutrient management strategy sit. Okay, so jumping into next generation urban greening. So we know that cities are grappling with a lot of things in a crowded and really costly environment. And so cities in particular, are starting to turn to nature-based solutions or urban greening, and particularly those that can provide multiple benefits across the landscape. Things like runoff reduction and flood protection, supporting biodiversity and heat mitigation, as well as providing human health benefits such as air quality improvement, access to nature, and well-being support. So today we're going to talk about a few different pieces of this project, looking at the multi-benefit landscape scale approach, which we developed for this project in San Francisco. Then we'll talk about 2 different case studies, one in San Francisco and one in Oakland, around the green and gray solutions to water quality improvements and other benefits. And then we'll look at some monitoring results from green stormwater infrastructure units, as well, and then we'll finish up with some challenges that we're finding in the Bay Area to urban greening, and some of the resources and approaches that folks are taking to try to deal with those challenges. So there are a number of drivers in the Bay Area that are driving this push towards multi-benefit urban greening, just, besides that crowded, costly space in the urban environment. In the Bay Area, one of the biggest drivers of green stormwater infrastructure in particular is the Municipal Regional Stormwater Permit, or the MRP for short. And the MRP is set up so that the number of GSI units that each municipality is sort of slated to install is based on a reasonable assurance analysis, looking at the reduction of PCBs and mercury by those units. And so the MRP is very focused on green stormwater infrastructure for those reductions. But the Water Board is willing to be flexible in their approach to thinking about how runoff and pollution is mitigated in the region, And one of the things that they point to that I just wanted to highlight for this group is the state of Washington's NPDES permit for large and medium MS4s in particular, and that more regional scale approach to reducing impervious surfaces throughout the watershed. We also have a number of city and county initiatives that are driving folks in the Bay Area towards the multi-benefit greening side of things, including urban forest plans, biodiversity and climate resilience strategies, a number of mitigation projects, particularly focused in riparian areas, as well as the need to address equity issues. And then finally, a lot of the funding for green infrastructure is coming from external sources, so either the federal government or the state of California. And a lot of those funding requirements these days require that multiple benefits are being addressed in these urban greening projects. So I'm going to start off with telling you a little bit about an approach that we're using for multi-benefit urban greening to help in that planning stage. And this work is focused in the Eslays Creek watershed in San Francisco. This is the biggest watershed in San Francisco, and we chose this watershed because the San Francisco Public Utilities Commission initially approached us to ask if we could help with a study that would help in a mitigation plan that they were developing. And I'll talk about that case study in a little bit. But this multi-benefit approach, we built on that work that we had done for the Public Utilities Commission. And one of the things that we are trying to do through this Next Gen Urban Greening project is to communicate to municipalities the benefits of planning at different scales, and particularly moving beyond just the site-based planning to watershed and city and regional planning. And so a lot of green infrastructure projects are really planned at a project by project basis at the moment, again, really driving towards meeting the criteria of that municipal stormwater permit. What we're trying to do is to use a watershed approach in this case, looking at the Eslays Creek watershed, to show how this analysis can be used to help prioritize locations for green stormwater infrastructure and other types of urban greening that really provide benefits where they're needed most, rather than trying to put a whole bunch of benefits into a project at a place in the landscape where they're not actually needed. So just a quick overview, and I'll dive into this a little bit, but wanted to give you an overview of where we're going. So in this example, what we did is we developed scenarios that were optimized for water quality. So this means we're using a co-benefit approach where the initial focus is water quality. And then our analysis focused on 3 additional benefits: biodiversity, urban heat, and canopy equity, to see where the need for those benefits overlapped with water quality. And then the goal was to select one optimal GSI scenario that generates the greatest overall benefit in light of these 4 benefits together, rather than just water quality itself. So what does that look like? So what we did is we started, again, focused on water quality. We used a tool called Green Planet, which was developed by SFEI. And the underlying model for that is a stormwater management model, or SWIM, that simulates stormwater and PCB runoff on a baseline condition without GSI on the landscape, and then these scenarios that have different GSI locations identified. There's also what's called a scenario locator tool built into Green Planet, which generates GSI scenarios based on feasible sites for different types of GSI features. And in Green Planet, we currently have 5 different types of GSI that include permeable pavement, flow-through planters, street trees, bioretention, and flow-through planter boxes. So then once those GSI features are identified, where they can go on the landscape, then Green Planet generates a number of scenarios that are looking at the effectiveness of surface runoff and pollutant load reduction against cost. So what that looks like, here, these figures on the left here are showing surface runoff reduction in the blue against cost, and then PCB load reduction in percent against cost on the x-axis there. And these green dots along in that PCB plot, those are the dots that are at what we call the efficiency frontier, right? So this is where you're getting the most load reduction for the lowest cost. Okay, and so then the map on the right here is just an example showing, you know, what a scenario looks like as it comes out of Green Planet. So this is the Slays Creek watershed, and these different colors here are just showing the different numbers of, in this case, bioretention cells that are assigned to each of the subcatchments within this watershed. And the turquoise, these are just the numbers. So this is 1 to 5. The orange is 6 to 10, and the dark blue is 11 to 25. And so this is just an example of how these scenarios are mapped out on the landscape in Green Planet, or as a result of the Green Planet output. Okay, so then we did a similar, so then we looked at these other co-benefits that we were interested in: biodiversity, canopy equity, and heat mitigation, and did a similar mapping exercise to identify where those benefits are most needed on the landscape. And I'm just going to zoom in on biodiversity here so you can see what this looks like a little bit better. So for biodiversity, this is an analysis that we do at SFEI as part of our urban biodiversity framework. And what the biodiversity analysis looks at is current habitat patches that are already on the landscape, and then the potential for connectivity between those habitat patches. And so the spatial priority score for biodiversity is highest, so meaning that that's where additional habitat would have the greatest impact on biodiversity, is shown in these dark green patches. And that generally tends to be in areas that are closest to existing habitat already, or in areas where additional habitat could be bridged by species in the system. Okay, so that's biodiversity. And then what we do for each of those co-benefits is then we also assign a GSI feature benefit factor score. And because, right, for each of these 5 different types of green stormwater infrastructure, they don't have the same effect, in this case, on biodiversity. So here, a street tree has the highest value, a tree box and bioretention have the next highest value for biodiversity, and something like permeable pavement, right, provides no biodiversity benefit whatsoever. So that receives a score of 0. And then for each subcatchment, we assign the number of GSI and types. We multiply those all together to get a subcatchment biodiversity co-benefit score. And then what we can do is we can combine all of those 4 different types of benefits to generate a total subcatchment score, and then start to evaluate which scenarios provide the most benefit across the landscape. And so, again, this is an example of where we've overlaid the benefits of green stormwater infrastructure with biodiversity. Okay, and you see here that the darkest green areas on the map are showing where the overlap of water quality or green stormwater infrastructure and biodiversity are the highest. So those are the places where, if you were to implement green stormwater infrastructure projects, the likely benefit to biodiversity is very high. So then the next step is to combine all of those together. And this map is a little bit, there's a lot here, so I'll walk you through it. So the first, so the blue areas, those are the number of overlapping co-benefits with water quality, where those spatial priority scores are greater than 80%. So the light blue is where there's one additional benefit in addition to water quality, and the darker blue are showing where there's 2 and 3 of those co-benefits associated in those places with green stormwater infrastructure. The orange areas are areas where green stormwater infrastructure was not identified by Green Planet. So there isn't great stormwater runoff value in those areas, but those are places where those co-benefits are overlapping with each other. And again, the lighter color is just where there's one of those co-benefits. The darker colors are where there's multiple co-benefits stacked on top of each other. And then the areas in gray are showing where water quality is the only benefit that would likely be provided in those areas. So those are kind of the least helpful scenarios if multiple benefit is what you're going for, right? And then the other way that this map can be used is in looking at where the blue and the orange and the gray, where all of those areas intersect. So for example, if you have a dark gray area, like in this inset up here, that's an area, right, where if you implement green stormwater infrastructure, the benefit is likely to be only to water quality in that space. But in the parcels near to that, right, there are other benefits that could be provided by other greening features. And so this sort of points at the need at some point for there to be some collaboration and coordination for co-locating projects that can provide multiple benefits, maybe not in the same footprint, but adjacent to each other. So this is really, a planning level tool. There needs to be additional ground truthing to vet the locations where these types of projects and benefits are actually implementable, and then work forward from these, from this type of a planning level analysis to identify what are the highest priorities for green stormwater infrastructure. Okay, so next I'm going to move into the first case study of green versus gray infrastructure, and this is in San Francisco. So this is the same watershed footprint as Leyes Creek, and in this instance, again, the San Francisco Public Utilities Commission had a mitigation order to deal with excessive stormwater runoff that was resulting in sewer overflows during heavy rain events. And the gray infrastructure approach to solving that problem was to increase the number of sewer pipes in this area that could take the water, get the water off the surface. But PUC was interested in looking at other types of interventions, particularly green interventions that could reduce runoff in the system without having to do extensive gray infrastructure updates. So this project was focused in two areas. One was called Soak It Up, that was really focused on tree planting, and then in the Alamany corridor, or the Slow It Down area, where trees and additional habitat improvements were recommended for the area. So the approach that SFEI took to investigating what some options here, we're looking at, again, the increase in tree canopy cover and converting impervious surface to vegetated cover for two different types of benefits. First, the human community benefits, looking at particularly public benefits distributed across the public area, the project area, that were really focused in the public realm. So mainly along sidewalks and streets. And then the second were biodiversity benefits that were focused largely in the Alamany corridor, which was an area that had much more space for additional habitat to be provided. And then also looking at increased connectivity and the effects on biodiversity in those areas. So we generated 3 different scenarios for this work, focused on, again, mostly focused on trees, and a low tree, a moderate tree cover, and a high tree cover scenarios. For the results that I'll show you, I'll focus on the moderate tree cover, where about 2,400 new trees were projected to be added within the watershed. About 1,600 of those going to the Soak It Up area, and about 800 going to the Alamany corridor or the Slow It Down area. Okay, so the first thing that we looked at was the change in maximum temperature in the study area. And so this is just showing an example for one block, and the areas there are sidewalks for each block. The map on the right, or sorry, the map on the left is showing the tree canopy cover under the moderate tree scenario. And then on the right-hand side, that map is showing the maximum temperature for the moderate tree scenario. And then what those colors are showing is how this scenario differs from the baseline based on the current tree cover of that block. So in this block, sidewalks on average, there's sort of a 2 to 10 degrees cooler based on where that canopy cover is happening, and on average 2 degrees Fahrenheit cooler. And I should say this analysis was based on temperatures that were during the 2017 heat wave in San Francisco, where temperatures were over 106 degrees. And so looking at how these heat waves are mitigated by canopy cover in the area. And then if we look more closely at the Alamany corridor, where again, more trees, there's sort of more space for these habitats to be happening. Again, looking at the change in the maximum temperature, we see with the increased tree planting here that there was about a 10-degree Fahrenheit cooling in parts of the Alamany corridor during heat waves. So a really significant change just with that tree planting in the area. We also wanted to look at where this increase in canopy cover would be occurring. And for the moderate tree scenario, most of that canopy cover would be in areas with a moderate to high environmental justice burden. So again, this is in areas that are providing the potential for access to greenery and other human health benefits, in addition to heat mitigation in those areas. This green approach would also create an additional 33 acres of vegetation, which again increases green space as a function for habitat for plants and wildlife. And then using this, that increase in habitat, we did an analysis looking at bird communities in the Alamany corridor, looking at two different types, urban adapted species and urban sensitive species. And using that increase in habitat, modeled what the likely population change would be for these different species. And we found that for urban adapted species, many constant or decreasing likelihood of presence without additional habitat, while the urban sensitive species had an increased likelihood of being present in the area. So those were the types of analyses that we did for this project in this corner of San Francisco. And the Public Utilities Commission took that back to the Water Board and presented both options. Unfortunately, due to a time constraint, the Water Board went the route of the gray infrastructure, but they were very interested to see the results of this study, and hopefully they were not against it. And so hopefully this has a good potential to be implemented for future actions. So Alicia, I'll turn it over to you to talk about the case study for Oakland.
Yeah, thanks, Liz, for all that information on Green Planet and how other analyses can complement the modeling work for our next gen project. I'm going to diverge momentarily from the next generation urban greening project to provide a little information about a case study we're doing that involves another way to consider incorporating multiple benefits into a green infrastructure siting and optimization tool like Green Planet. In this case, by bringing in community input, by adding weight to such input in addition to other benefits. So in this community, and probably most, it's not about gray or green infrastructure to manage stormwater, but rather a combination of the two. So the case for this, which is the case for this underserved community in deep East Oakland, we got a grant to embark on a community engagement series to develop a greening plan for their community to address some of the stormwater challenges they face. This grant involved other aspects of the project too, but I'll just talk about the engagement series. So some of the issues facing this neighborhood was flooding along a creek. Let's click forward and let's see if, nope, go back. Sorry, I just added some animations that didn't come through. So anyway, there's a creek kind of in the middle left-hand corner. Yeah, nice. That's a small drainage area going up from there, Melissa. So they get a lot of flooding in people's backyards here. There's flooding in the streets. There's a whole area in the lower right-hand part of the watershed or the drainage area that doesn't have any gray infrastructure at all. So they get a lot of flooding or ponding in the streets. There's just a general lack of urban greenscape. They have urban heat island effect. So I want to recap a little bit of our engagement work and how it informed our Green Planet model runs. So first, go ahead and click forward. This is a recap of our first 2 engagements.
Let's quickly recap the Community Greening and Resilience Workshop series. Yay! We kicked it off with a workshop where we went over the project and what green stormwater infrastructure is. We worked with residents to identify strengths and weaknesses in the neighborhood as they currently exist. After residents shared out, we broke bread and then went over a 3D model tool created by SFEI to help us with our visualization. Second, we did a neighborhood tour around the DAG community to ground truth the strengths and weaknesses that we heard from Workshop 1 through a photo voicing activity. Residents and city staff provided neighborhood history and together identified potential areas on where GSI might be ideal. After ground truthing the weaknesses and strengths of the neighborhood, we broke bread, filled out surveys, and residents got prepared for the next workshop.
Okay, go ahead and forward it, Melissa. So in subsequent engagements, we continued educating the community about different types of green infrastructure, and then we worked with the community to identify where they would like green infrastructure, where they see green infrastructure would be ideal. And what was really clear was how these participants were experts on their community, right? And they could weigh in on the trade-offs of green infrastructure in a way that an outsider really had no idea about. Go ahead and forward, Melissa. So where they wanted to see green infrastructure was heavily informed by the strengths and the weaknesses that they had initially worked on synthesizing and conveying to us in the first couple engagements. Move forward. So the way we brought Green Planet in was firstly to help ID the locations where GSI was feasible. So in this case, portions of the community had relatively high groundwater, so certain types of green infrastructure was not ideal. And we brought this information back to the community for them to consider. And using that information, they reiterated on their desired locations for green infrastructure. Next slide. And then finally, using the optimization tool for Green Planet, we developed a couple of green infrastructure plan options that heavily weighted the community's input while working to optimize either tree canopy or stormwater volume reduction, which were 2 of the greatest weaknesses that they identified for the community was urban heat island and then flooding. Next slide. So, excuse me. After developing these optimized scenarios using Green Planet, we took these potential scenarios back to the community again to have them weigh in on which of the plans, the one optimized for tree canopy or for volume reduction, which one of those plans was the most desirable when they saw it on the map, when they consider, and in the 3D model, when they really considered the trade-offs associated with each one. So for example, more trees in the landscape. A lot of times the cities can't always take care of those trees, so it falls on the responsibility of the homeowners. So there's trade-offs, right? There's also lost parking spaces due to some of this green infrastructure, and the community could weigh in on what they were willing to give up or willing to take on as a responsibility in exchange for these added benefits. So this was an example of how we expanded the use of Green Planet to add in the weighting factor for community input. So now I'm going to go back to our next gen project and give you a little teaser of the data results so far. So back in San Francisco now, for the same project, we got to look at monitor 4 bioretention units. So each drainage area, we refer to it as a DMA, a drainage management area, drained either a parking lot or a directly adjacent street within a residential or commercial area. The bioretention unit size to the drainage management area ratio ranged from 2%, which we consider a bit undersized, all the way up to 22%, which we consider pretty oversized, actually. In terms of optimal volume reduction, in terms of optimal sizing, not going too big, but getting a set amount or a set amount of volume reduction per storm. So each of these units contains 6 to 10 inches of ponding depth, then 18 to 21 inches of soil media, and then a gravel bottom with an under drain. Next slide. So we sampled at the inlet and the outlet for each of these units. That was the main part of the project. And we looked at a variety of pollutants, including metals, PCBs, pesticides, dioxins, and then the University of Washington CEC suite that Ed Cologier's lab does. And so I'm sure some of you are familiar with that suite. And then in addition, we looked at TSS and microplastics. I have a little asterisk on the outlet, the word outlet, because for especially those oversized units, we didn't always get outlet flow. So that was kind of disappointing for us, but also, well, that's so great that it captured 100% of the volume, right? In any case, we did a couple other smaller sub-studies where we collected soil profiles at 3 sites to see where pollutants in the depth of the soil, where those pollutants were being captured, which could have impacts for maintenance. And then also we measured, mercury is a big driver here in the Bay Area. So we measured mercury for a subset of storms on grab samples that we collected over the course of the hydrograph, so that we could look at the pollutograph. And then also on another subset of storms, we looked at mercury on different size fractions. Next slide. So here's just a quick teaser of the results. And depending on how familiar you are with green infrastructure studies, you might think none of these are actually overly surprising. So TSS, total suspended solids, was captured pretty well. This is a subset of the data that we have back so far. So, and I haven't done a lot of analysis on it, so I'm just showing you some really basic graphs here. But yeah, so TSS was pretty well captured. It, let's see, it ranged from 60 to 99% reduction in concentrations, but then there's also volume capture, so that would decrease the load even more, right? We are going to model flows to estimate decrease in loads overall. Next slide. For PCBs, I think that's important up in your neck of the woods. Again, PCBs were pretty well captured at all the sites, except for the sites where, like that first sample on the far left, where concentrations of PCBs, the inlet concentrations, were very, very low. We find that there's oh boy, now I'm forgetting the term, but it's hard for the PCB, the outlet concentrations, to go lower than a certain point. Somebody can put it in the chat if you know the word I'm talking about. In any case, but otherwise concentrations decrease between 14 and 95%. Next slide. Total copper, not so much. So the gray bars are the outlet concentrations, and you see the outlet concentrations were actually pretty high, higher than inlet concentrations in a lot of cases. And this was driven a lot by the dissolved copper concentration. We have dissolved copper results as well. So we're still looking into that, especially what's going on at the VV site, which is our Visitation Valley site, where total copper concentrations on the outlet are quite a bit higher than the inlet concentrations. Finally, for my last 3 quick slides, we worked with the Colloget Lab at your University of Washington to look at a suite of CECs. And the next 3 slides are for the tire and road wear associated contaminants that we kind of look at kind of most closely. So one is diphenylguanidine. Am I on the diphenylguanidine concentrations from inlet to outlet decreased pretty significantly. Next slide. I'm going to take a stab at this one, hexamethoxymethylmelamine. At SFEI, we like to call that And you'll notice it also had pretty good reductions in concentrations, again, with decreases in flow as well. That would mean capture of load would be even greater. And then finally, of course, 6-PBD quinone. But a note here, the US EPA acute aquatic life screening value is 11 nanograms per liter. So that's expected to be generally protective of freshwater species, including sensitive salmonids that are exposed to 6-PBDQ for short durations. Now, all of the inlet concentrations are well above this value, which is unsurprising and consistent with other monitoring done by SFEI, but others all along the West Coast, including a lot of you up there. So showing urban runoff consistently exceeds toxicity benchmarks. Although you can see that the bioretention units did reduce the concentrations quite a bit, the outlet concentrations for half of the site storm combinations still exceed the screening value. So these particular designs may not be sufficient to fully protect sensitive surface water ecosystems from 6-PBDQ toxicity. Okay, so that's just the teaser. We're early in our analysis, so we hope to produce a couple of reports or manuscripts by the end of next year. So stay tuned. Melissa?
Great. Exciting to see those data. I haven't even seen them yet, so very cool. All right, so the last bit here, I just wanted to focus really quickly on some of the challenges that we're facing in the Bay Area around multi-benefit urban greening. And, some of these may be shared by you all as well. And so, interested to learn, kind of how these challenges, like, are they similar across regions, or are they really different? So some of the things that are particularly challenging, and again, I'm focusing in this multi-benefit space, is that cross-agency coordination. So, we have cities and counties and regional entities all working in really similar spaces with complex and confusing jurisdictions. And just, sort of getting that coordination to happen, it can be really challenging, particularly with high staff turnover. Having meaningful community engagement as part of these projects, we know that's a requirement for a lot of them, but really sitting down with communities and understanding what are their needs and the types of benefits that would be most useful is something that doesn't happen in a lot of these processes. Another challenge is just acknowledging that there are trade-offs for these multiple benefits. In some cases, there are really strict standards for green stormwater infrastructure, for example, that may preclude certain types of planting or design that would provide those multiple benefits. So understanding what those different trade-offs are. And then also needing guidance in terms of designing these different features to provide those multiple benefits, and then also maintenance. How do we keep these features how do we upkeep them to make sure that they continue to provide these benefits going forward and don't lapse into states of disrepair. So as part of NextGen, our project, we've also convened a regional forum, and that's where we're working through a lot of these different gaps and trying to identify some resources and strategies that folks can use throughout the region to really advance multi-benefit projects. So some of the gaps that we're seeing in design here, the first one is just how do folks use native plants in the urban setting? Sort of moving from this model of turf and non-natives to native plants, and lots of questions around designing for that, particularly in our region where a lot of the natives, they don't look great all year long. And so thinking about that design and what that looks like. Minimizing maintenance costs is a really big factor in design and changing how design is done. People are really worried that maintenance costs will go up. Just how do you design to provide multiple benefits? This is evolving, and additional co-benefits with stormwater infrastructure as well. And then the final one, just connecting us across projects. So how do we move beyond just this project by project planning and think about what are the benefits that we're providing across the landscape, and how do we make connections between those projects? Again, kind of harkening back to that planning map with where those different areas are where multiple benefits could be provided. And then on the maintenance side of things, this is another area that folks are really struggling with, in part, sort of changing the framing and the planning and the funding around green infrastructure maintenance versus gray, right? It's really different. It's really different than maintaining turf. And so, kind of getting people to change their thinking around what that looks like. Staffing and workforce development is a big issue. Again, these are more complex maintenance needs for these different types of planting. Maintaining multiple desired benefits and native landscaping. Adaptive management is something that people are really interested in, but don't have great guidance on. And then also monitoring performance metrics long-term, again, in the context of water quality in particular, but also these other benefits. Are we actually generating the benefits that we think we are? And then coordinating that maintenance across agencies. And so through this regional forum, some of the resources that have been identified by folks for filling some of these gaps include things like native planting palettes that are developed by folks like us at SFEI, but also the California Native Plant Society. And some of those recommendations in particular based on the historical ecology of the area, what used to be here, or what does really well in these different types of habitats. For example, in San Francisco, the western part of the city was all sand dunes, so what does well in that habitat, based on that historical ecology, and what functions do those bring to the landscape. We're working with agencies to develop a plant performance tracker, and particularly focused on native plants, but also for different typologies. So thinking about what does well in a bioretention unit versus what does well in a schoolyard. Those are really different things, and understanding how those different types of plants, sort of are paired with the uses, the intended uses of those spaces is something that's really important to understand. We've seen some examples in San Francisco in particular around multi-agency coordination for maintenance. So bringing together multiple departments that are doing the maintenance. It's not one group isn't doing the maintenance, to learn from each other and to coordinate what they're doing. We have other cities that have developed checklists for maintenance that include photos, and those guides are being produced in multiple languages to help their maintenance crews understand the importance of these different urban greening features, why maintaining them in certain ways is important, and particularly what the regulatory requirements are for green stormwater infrastructure. And then finally, we're developing resources around community outreach and education, based on things like the project that Alicia talked about in Oakland, other work that we're doing around the Bay Area that really center that community outreach and engagement to help build those resources for cities and municipalities. And just to plug, last thing for the project that we're working on, we're developing a regional framework that will bring all of these pieces together to try to help the region advance this multi-benefit green infrastructure in the Bay Area. So with that, hopefully we've left enough time for questions, and I'm gonna stop sharing my screen just so that I can see everyone, because I can see no one right now.
Sounds great. Thank you. Feel free to continue dropping questions into the chat. Otherwise, you're welcome to raise your hand and we'll unmute you. In the meantime, we've got some questions already, so I'll call those out. One is about thinking about structural diversity below trees and the importance of that, and thinking about how you look at how much is possible, kind of the maintenance considerations and the long-term survival when you're thinking about those benefits.
Yeah, that's great. So yes, in the design guidance that we generally provide, we are trying to get folks to think about that structural diversity as well. So it isn't just about the tree, but that's one of the easier ways for us to model, right? Particularly, rainfall interception on the landscape. Assuming that, kind of the area below it now is a pervious surface instead of an impervious surface. But yes, it's really important in the design to do that structural diversity and have shrubs and low-lying and, to really work with, again, this all comes back to the maintenance staff in understanding what works and what doesn't. One of the things in San Francisco that we hear a lot about is just safety and aesthetics, and not having a lot of, shrubs where potentially, people don't feel safe, where there are lots of big plants close to pathways and things like that. So yes, definitely a consideration though.
Great. I appreciate that context in terms of how you're thinking about it from modeling, but then how it gets implemented with that subsequent design guidance and community input. Joel, I see your hand. Go for it.
Thank you. Thanks for this presentation. My question is about the first part of the talk where you were doing that really elegant GSI work and choosing the individual parcels and thinking about that. I think it's really an elegant way of approaching it. I was taken a little aback, but then you said, but they didn't adopt it. They used the gray stuff. And that happens a lot. I'm just wondering if you could say a little bit more about kind of that decision point for them. Was it, you said timing, and is it just a difference in construction cost or timing, and they're under a court order or something to get a faster result? Maybe if you could comment a little bit on cost as well between the two approaches. Thanks.
Sure. Yes. So I can, yes. So it was a mitigation order to reduce stormwater and stormwater flow. And so the time component was, yes, it's going to take longer to implement the green solution than it would be to do the gray solution. And so that's ultimately where the water board made that decision, was based on that timing and the need for those effects to be mitigated sooner than later. In terms of cost, I don't think I can comment on that. Yeah, we didn't do an analysis of cost in this example. I think the Public Utilities Commission did do some work on that. And Alicia, I don't know if you have any other context to that. But I can't speak to that.
Yeah, thank you.
Yeah.
Alicia, this question's maybe for you, and it's around from the monitoring that you've done at these very specific sites, how that treatment compared to what the model would have predicted. And then the second piece related to this is just, is there any insights in terms of the long-term ability for treatment and how that might change over time?
Yeah, thanks. Yeah, and Melissa, correct me if I'm wrong here. I'm not an expert on the Green Planet, but in terms of identify or estimating our PCB or other pollutant load capture using the Green Planet model, we have to input potency factors or concentrations, if you will, of reduction. And so what we did to do that for, let's talk about PCBs specifically, is we took data from previous studies around the Bay Area and elsewhere, and kind of estimated a general concentration decrease. Is that correct, Melissa?
Yes,
and then,
yep.
and then we kind of apply that widely. So this new data that we've just collected will be added to that former data set to help further improve it, or at least improve the certainty. But I will say, for PCBs specifically and TSS, the results were not all that surprising and in line with all of the results that went into the potency factors for the model. So, you know, when you're seeing 80 to 99% reductions in PCBs, that is pretty consistent with what we see, especially when those concentrations at the inlet are significant enough. Again, when they're very low at the inlet to begin with, there's just not a lot of decrease you can still get. Because there is this lower threshold in a lot of cases, and I'm sorry I'm blanking on the term, but in any case, to respond to the second part of that question, I think it's about the the longevity of the GSI in terms of mitigating various pollutants. Well, I don't know exactly. That's I don't know exactly. What I do know is there's a lot of concern about these units kind of acting as mini toxic sites, right? That are where they're capturing a lot of pollutants, and then people are somewhat worried that they'll be very toxic. And as when we looked at the soil profiles and estimated the total mass at different depths of the profiles, what we found is even at the surface, where a lot of the pollutants, let's say for PCB specifically, were being captured, they just filter out right at the top to a large degree. Well, when we compare those concentrations to the residential screening limits for the US EPA, for most sites, we were talking on the order of 10 to multi-hundreds of years that before the soil would need replacement. So there was one site where there were very high input concentrations, and so it was after a handful of years or so that they should have replaced the soil in the top right in front of the inlet, where PCBs kind of drop out pretty quickly. Throughout the rest of the body of the unit, it was I forget exactly, but maybe 20 or 30 years. So, I hope that kind of answers the question. I don't have perfect answers, though.
That's fair and great to still have a general sense of magnitude, and also some considerations to keep in mind in terms of even where in the green stormwater infrastructure to be thinking about doing that soil replacement. We also have a question just about climate change and how you're thinking through that in this analysis and in this large scale planning.
Yeah, great question. So one of the things that we did with this, our Green Planet analysis for San Francisco, is instead of using the design storm, which the municipalities use for looking at the assumed benefits of green stormwater infrastructure, we used a 2-year interval storm, which the municipalities don't love because it's a bigger storm. And so, some GSI features are less effective at that bigger storm than what they're designed for. But we wanted to do that just in recognition that we're likely to see more intense storm events here in the Bay Area as a result of climate change. So that's one way that we brought that in there. Another way, more, I guess, in a qualitative way, is that as we develop plant palettes that include trees and shrubs, and we have been working on developing a climate resilient tree list for the Bay Area in the hopes that, again, those trees are resilient to climate change so that they're able to provide those benefits that the canopy can persist for for many years, and that cities aren't having to replace trees frequently, which then, of course, people don't want trees if they're not living, and kind of sets us back in that space. So.
Yeah, I appreciate that. I'm going to do one more question before we wrap up, which is just how are you thinking about after you have the results of these prioritizations, working with municipalities and others to actually get projects in the ground and implement, recognizing that there are challenges like timing with consent decrees and others?
Right. Yeah. So with this project in particular, we continue to work closely with the Public Utilities Commission to talk through these results and, to make sure that they're understanding kind of what we're trying to do and how that fits into the processes that they're working through in terms of their own green stormwater infrastructure plans. So all of the municipalities around the Bay have had to develop green stormwater infrastructure plans. And so just, sort of thinking about how this work fits into there. We're building on this project and starting a new project in Santa Clara County, so in the South Bay. And again, doing a similar type of analysis, but connecting really closely to the stormwater municipality there, and figuring out how we align, sort of this landscape scale approach with their analysis of individual locations for GSI, in the just to see, like, do we need to shift priorities, or would it be beneficial to shift priorities? And again, based on funding, where those multi-benefits need to be and how they can implement those projects.
Right. Well, I so appreciate both of you making time to share the insights and challenges and new things you're trying too, as we struggle with lots of shared realities when it comes to stormwater. For those on the call, I hope many of you will join us next month on December 3rd for our next roundtable. We'll be looking back in the Puget Sound at some of the cumulative effects, evaluating salmon restoration up in Whidbey Basin. And certainly as we're getting close to the end of the year, which is wild, please feel free to reach out to me with any recommendations in terms of topics or speakers that you'd like to see coming into the new year. But appreciate everybody's time today and the ongoing discussion. Thank you.